we're going to look at the operations radical expressions. This is page 79 of your handbook. And some of you guys have already been started working on this on Alex, but what I think you might like compared to Alex is that we could use kind of like a box to organize our information. And we've done multiplication like this before. So if we kind of go over to question number 5, if we want to multiply a binomial times another binomial, we can actually write each of the terms in a column, and then our other binomial, x plus 3, for each row. And then it's kind of like a multiplication table. We do 2x times x, that's 2x squared. Negative 5 times the x, that's negative 5x. 3 times the 2x, that's going to be 6x. And 3 times negative 5, that's negative 15. And we can simplify a little bit. I see my like terms right here. So my final answer for this multiplication will be 2x squared plus x minus 15. So we've already kind of done that before, but now what we're going to do is just involve some radicals into our operations. So if you look at question number 2, we can still write it that way. We're going to write radical 3, that's our binomial with the positive 2, and then we're multiplying by just a monomial, a single term there. So when we multiply radical 5 times radical 3, that will become a radical 15. They're both in radicals, so they get to come together as that 15. Now 2 times that radical 5 just gets written as 2 with radical 5 next to it. There's really a multiply, but we kind of drop that off. So we don't normally have that written, but that's what's implied. And again, this one was not written as radical 10 because 2 is not in a radical. And so there's no like terms here, which would become radical 15 plus 2 radical 5. There's just like nothing I can do with that. When we look at 3, we now have a binomial times a binomial. So let's write that out. Radical x minus 3, radical x plus 2. So radical x times radical x will become a radical x squared. Negative 3 times radical x will be negative 3 radical x. 2 times radical x will be 2 radical x. And then negative 3 times 2 will become a negative 6. And so similar to what you saw up above, we combined 6x and negative 5x to make that single 1x because those were like terms. And so down here, we have 2 of these radical x guys and negative 3 of these radical x guys. So these are going to be like terms as well, where we're going to get negative 1 of those radical x's left. Now, the square root of x squared can simplify to be x. So I'm going to just write x there, and then negative 6 goes here. So we can kind of see where everything comes from. And that would be my final answer. So on number 4, let's see how this works out. Square root of 2 minus the square root of 5. Square root of 3 plus the square root of 4. So this right here will become a square root of 6 because 3 times 2. Let's see, this 2 times the 4, that would be the square root of 8. 5 times 3, that will be a negative square root of 15. 4 times the 5, that's going to become negative square root of 20. Now, one thing I just noticed I could have done is kind of simplified. I already know square root of 4 is 2, and I could have used that. But since I missed that, I can go back over here and just simplify each of the radicals. So like square root of 8, I know is 4 times 2, and because that's how I made it, right? 4 times 2. And then 2 and 2, so that I can pull a 2 out. So this could become 2 square roots of 2. Similar here, this is 4 times 5. Again, that's how we made it. So this was 2 and 2. I get to pull a 2 out. So this would be negative 2 square roots of 5. 15 can't reduce. That's 3 and 5. No pairs there. And this is 3 and 2. No pairs there either. So I just know that there were pairs in this last row and that was going to happen because of that square root of 4. So my final answer here, I have square root of 6. I have negative square root of 15. I have 2 square roots of 2. and I have negative 2 square roots of 5. So here I don't have any terms that could combine together because I don't have any what we say are like radicals. So in order to add and subtract radicals, just like we add like terms, we have like radicals. And they have to have the same index and the same, we call it the radicand. That's the inside of the radical. And so we'll practice that a little bit below. So if you look at number 6, all of these radicals are radical 3. So they all have the same index, which is 2. There's like a square root in there, even though you don't see the number 2. And all of them have the same radicand, which is 3. So really, it's kind of like seeing like 2x plus 4x minus 5x. So if you had all of that, you'd say I got 2x's plus 4x's, that's 6x's, minus 5x's, then I'm down to 1x. But here, they're just radical 3's. So I have 2 of these things plus 4 of these same things minus 5 of those same things. So that's going to leave me with 1 of these radical 3's. Or you could just write radical 3. They're both the same. On number 7, just pay attention a little bit here. I have a radical 3 term here, and then another radical 3 term here. And then these are radical 5 terms. So we'll be able to put the radical 3 terms together. We have 5 minus 2, so that's going to be 3 of those radical 3's. And then we have 3 of those radical 5's plus, even though you don't see it, it's just like when there's like an x, there's a 1 in the front there. So we're going to have 4 of those radical 5 guys. And those can't combine anymore because they are not like radicals. On number 8, when we first start here, I'm like radical 3, but wait, they don't have the same index, so those actually cannot combine together. But when I look at 75 over here, I'm like, oh, well, maybe we can simplify that to make it look like the other one. So 75 comes from 3 times 25 works. 3 times 25, like 3/4, and that's 5 and 5. And so I have a pair of 5's that would get to come out, and 3 has to just hang out inside. So this is going to be 5 square roots of 3 minus 5 cubed roots of 3 plus, look at all these 5's and 3's. So the only actual like terms here are the 5 radical 3, because it has a radical 3, and this other 5 radical 3. So we're going to get 10 of those radical 3's minus 5 cube roots of 3. And again, that can't simplify anymore. Okay, for part 9, again, they don't look like radicals at first glance, but we'll try and simplify them to see if we can pull out some stuff and make them look the same. So 200 is 2 times 100, but 100 is 10 times 10. So you can take out that pair. You can keep going to the prime numbers, but as soon as you see a pair like that, you can pull that out. So that's 10, and then the 2 has to stay inside the radical. And then let's see, the x is just a single x. It has to stay inside. And then the y squared, that's just y. So we have a pair. It gets to come out as a single y. So this is 10y square root of 2x. On the other side here, we have 162. Well, that's 81 times 2. And 81 is, 9 times 9. So for that pair, we get to pull it out. Now, there's already a y outside of this guy, so I'm going to write that down with that negative. And so then this 2 doesn't have a partner. It has to hang out inside. And also the x doesn't have a partner. He has to hang out inside. But now we have like radicals. There's square root of 2x here and square root of 2x. Now they also have a variable outside with that y, so it's like that whole part has to be like. And so it's saying we have 10 of these guys minus 9 of these guys. So we're going to have 1 of those guys, which is y square root of 2x. Final answer. You could write it without the 1 if you'd like. And so we just have that y square root of 2x. When we flip over to the next page on page 80, we're going to notice a couple patterns, and they're going to be some patterns that we've seen before. So if you look at number 10, these are two binomials. Notice that they look the same, but different or opposite signs in the middle. So that should look kind of familiar. So I'm going to give you a couple minutes. You should try 10 and 11 and 12, push pause, and then come back. So now that you're back, let's rewrite this, kind of double check that you did it correctly. So I'm writing out my two binomials. So radical 3 times radical 3 is radical 9, but really that's just 3. And you could already know that because you have 1 3, 2 3s, so you know that it's going to come out as a single 3. Now we have radical 3 times 5. That's going to be 5 radical 3. Then we're going to take negative 5 times radical 3. That's going to be negative 5 radical 3. And then last, we have negative 5 times 5. That's negative 25. So if you look at this, right in the middle here, those are like radicals. They both have radical 3's on them, but one's positive, one's negative, so they're going to cancel out. Cancel out. They undid each other. So all that we really have left is going to be the 3 and negative 25. So it's 3 minus 25, which is negative 22. So then when we look at question 11, let's see. Again, it's identical binomials, but they have opposite signs in the middle. And so we're going to write it radical x plus radical y, and then radical x minus radical y. And so radical x times radical x, that'll just be radical x squared. So right away we can just say x. So radical x squared, which is x. When we take radical x times radical y, that's going to be the square root of xy. Negative radical y times radical x is negative square root of xy. And last, negative radical y times radical y is just going to be minus y. Or you could write it, there's your little baby step there. And so you can see, again, these two terms are going to cancel out. And so all that we have left is x minus y. So then part 12 says, okay, well, now that you did all that, what do you notice? So question 12 says, what do you notice about the products in 10 and 11? And so what I want you to see is that there are no radicals anymore. There's no radicals in here, no radicals in here. So no square roots anymore. And the reason why in that pattern that might seem familiar is the difference of squares. If you have a plus b times a minus b, maybe you're not used to looking at it that way, but if you look at a squared minus b squared, when we factored that, we said it would be a plus b times a minus b. So the same binomials, but opposite signs because it always canceled out the middle. And so you can look back and the middle was canceled in 11 and the middle was canceled in 10. And then what happens is that you really just take a times a, that's where the a squared comes from. And then you have the b times the negative b, which is negative b squared. And so you can see that happen. So one of the reasons why we want to see that pattern is that when you look at question 13, it wants us to rationalize, which means we need to rewrite an expression to contain only rational numbers. And so that means that there can be no radicals because radical 3 is not a rational number. Remember, rational number means that you can write it as a fraction of integers or like whole numbers, but they could be pluses and minuses. So like square root of 4 is rational because we can rewrite it as 2, which can be rewritten as 2 over 1. But square root of 3 is for sure not rational. So square root of 4 would be, but square root of 3 would not be. So if you look at number 13, when it says to rationalize the denominator, really it's saying we don't want to see that square root of 3 there. And so if we want to get rid of that, we can multiply by something. Well, if we take a look at number 10, we were able to multiply square root of 3 plus 5 times square root of 3 minus 5 to get something without radicals. I got rid of that radical 3. So we can do that over here on 13. We can multiply by the square root of 3 minus 5. But if we want to keep our fraction equivalent, remember whatever you do to the bottom, you have to do to the top as well. And we're allowed to do that because really we're just multiplying by 1. And so on the numerator, we're going to have to take 7 times square root of 3 minus 5. And then the bottom will be that square root of 3 plus 5 times square root of 3 minus 5, which we already know radical 3 times radical 3 is 3. Radical 3 times minus 5, negative 5, is negative 5 square roots of 3. But we also know we have positive 5 square roots of 3, so those cancel. And so then the last product we need is just 5 times negative 5, which is that negative 25. So we already saw this, but that would be negative 22. So we have rationalized the denominator, but let's write our final answer. We need to multiply the numerator. That will be 7 square roots of 3 minus the 7 times 5, 35. So 7 square root of 3 minus 35. This is beautiful. Some people like to take the negative to the top of the fraction, which you could do that too. So just another way that you might see the answer is negative 7 square root of 3 plus 35. So they took the negative to both of these terms, and then you write it over positive 22. So either of these answers are 100% right. Okay, so on number 14, we want to rationalize the numerator this time, which you can see the numerator is the one that has the radical in it. So we need to multiply by the exact same binomial, but with a plus. So it has to be opposite sign here. And if we do it on the top, we have to do it on the bottom also. So that is like we multiplied by a 1. So it's not changing the value, just changing what it looks like. So our numerator will have square root of x minus 1 times square root of x plus 1 all over x minus 1 times square root of x plus 1. So on top, we know that radical x times radical x is just x, and we're going to get a positive 1 radical x and a negative 1 radical x, which cancels. And so the last part will just be minus 1. Now, if you want to see that with the box, that would be totally fine as well. So just if you want to see that numerator, if we're going to multiply it, I just did distributing, but we can rewrite it. A lot of people like this because it helps organize everything. So we're going to get square root of x squared, but that's just x. We'll get negative square root of x there. Here's that positive square root of x. And then 1 and negative 1 is negative 1. So you can see these guys cancel, the middle terms cancel. And so we're left with just the x minus 1, which is what we got on the top there. Now on the bottom, we could distribute that, but right away I'm noticing that these guys, we have an x minus 1 and an x minus 1 on the bottom. We could just reduce those. So that could just be a 1 right there. So our final answer could just be 1 over square root of x plus 1. So that would be perfect. Now, if you didn't notice that, which is totally fine, you probably would have multiplied the denominator out. And so that would be x minus 1 times square root of x plus 1, which would become, this will be x square root of x this time. This will be a negative square root of x, and that will be a positive x minus 1. So it looks like my numerator would be x minus 1 over x square root of x minus square root of x plus x minus 1, which at first glance doesn't really look like anything could simplify. This x minus 1 and this x minus 1 are not able to reduce because it's not factored. They're just added together. So you could say that that's your final answer. You're just missing a little bit of simplifying, but it's still good. This is just pretty neat if you notice the x minus 1s, because then right away you're a lot simpler, but both of them would be acceptable. Okay, so number 15 wants you to try and rationalize the denominator of this fraction. So also make it a little bit simpler. It's just a single term on the bottom, that square root of 50. And so before you keep watching, I want you to pause it and think about how you might try and rationalize this. So there's lots of different ways. So we want to try and come up with at least 2 different ways that we can rationalize or get rid of that radical 50 in the denominator. So pause it and try. Now that you've tried, let's see. One thing that I might think about is just multiplying by square root of 50, because then I would have my 2 50s that would be able to come out. So on the bottom, we have 50 and 50, so it could just come out as 50, or maybe you actually multiplied it, and so you say, oh, well, 50 times 50, 50 times 50 is 2,500. So we have, oopsie, not erase. We have the square root of 2,500, but really that was 50 and 50, so you have your pair, or maybe you want to keep going to the prime factors, 5 and 10, 5 and 10, 5 and 2, 5 and 2, so you could think, well, I have a pair of 5s, that would come out, I have another pair of 5s, that would come out, and then I have my pair of 2s, that would come out, with nothing left inside, which is really just 50. But again, if you notice radical 50 times radical 50, the same thing times itself, you can just go right away and take it out because you have your pair. Now 7 times square root of 50, one's in a radical, one's not, so they're just going to sit next to each other. So we have 7 square root of 50, 7 square root of 50. Now before I finish this off, I do want to make sure all my radicals are simplified. So radical 50 is 5 times 10, which is 5 times 2. And so for this pair of 5s, I'm going to pull it out. And there was already this 7 outside, so I'm going to have 7 times that 5. And my little 2, my last factor, has to stay inside. So we'll have square root 2. And then that's still all over 50. So that's 35 square roots of 2 over 50. But 35 and 50 can reduce because they both have a 5 in common. So that would become a 7 radical 2, since 35 divided by 5 is 7. And 50 divided by 5 is 10. So this would be my final answer. Again, there's lots of ways you could do this. I see that happen a lot. Another thing that some people might have thought of, maybe you did too, is to simplify the radical first before you even try and rationalize. So we know square root of 50 is 5 and 10, and that's 5 and 2. And so you say, okay, well, I have my pair of 5, so that gets to come out. And my 2 doesn't have a pair, so it has to stay inside. And 7's still hanging out there. And so right now you might say, oh, well, I don't need to get rid of square root of 50 anymore. I just need to get rid of a square root of 2. So then let's multiply by square root 2 instead of the 50s. And what's nice about this is you're dealing with smaller numbers. That'll be 7 radical 2. And on the bottom, 5 radical 2 times radical 2. Well, you see your 2 pairs. Or you see your pair, so it come out as a 2. Maybe you didn't see that, though, so it'll be 5 square roots of 4. Because radical 2 times radical 2, but really that's just 2. So 7 radical 2 over 5 times 2, but that's 7 radical 2 over 10, which ends up being the same answer. So there's plenty of different ways that you can try and rationalize this. There's just sometimes some different ways that might be simpler. So, and you might have even tried it another way, but your final answers would all be the same once you finish simplifying.